ScaleDojo.dev. In today's video, we will be constructing a high-level design of a scalable newsfeed system similar to Facebook, Instagram, or Twitter's homepage. Now, the purpose of a newsfeed system is to display posts from users that I follow, ordered by recency and relevance. Now, according to the given requirements, after we go through the design specifications, we can see that the system serves around 500 million daily active users, experiences a 100:1 read-write ratio, and should load a user's feed in under 300 milliseconds. Now, since the system is heavily read-oriented, our architecture follows a cache-first approach combined with asynchronous fan-out processing. Now, let's get to the actual design part. First, we start with the client. As we know, everything begins with a client. The client could be a mobile application or a web application. Whenever a user opens the application or refreshes the homepage, the client sends a request asking for the latest newsfeed. Now, instead of directly contacting the backend services, the request first reaches the load balancer. So the next component in line is the load balancer. The load balancer distributes the incoming requests across the multiple backend services that we have. After the load balancer, we have an API gateway. The API gateway acts as the single entry point into the backend system. Before forwarding any request, it performs common responsibilities such as authentication, authorization, request validation, rate limiting, logging, and request routing. By centralizing these operations inside the gateway, the backend services remain focused only on the business logic. After completing these checks, the API gateway forwards the request to one of our feed service instances. So next we have our feed service instances. Now, in an architecture, we can have multiple feed service instances, but since we have a budget limit, therefore we are only taking 2 feed instances here. Now, the feed service is the core component of this architecture. Every main business logic is present inside this feed service. After the feed service, we have a main database or the SQL database, and we also have a cache memory. Whenever a request reaches the feed service, the first thing it does is check the feed cache. This is because it is a cache-first architecture, and hence our cache memory is always consulted before accessing the main database. If the requested feed is already available inside Redis or our cache memory, it is immediately returned to the client. Since our cache memory stores data entirely in memory, this operation usually takes only a few milliseconds, thus allowing us to achieve our target response time of under 300 milliseconds with ease. However, if the requested feed is not found inside our cache memory, we have a cache miss. In that case, the feed service queries the SQL database to retrieve the required posts and construct the user's timeline. The SQL database acts as the single source of truth whenever the cache data is unavailable. So here, the SQL database stores all the main and permanent information which is required by our system. It contains posts and structured information necessary for generating user timelines. Whenever the feed service cannot find a feed inside our cache memory, it retrieves the required information from our SQL database or main database. Although database queries are slower than Redis lookups or cache memory lookups, they provide durable storage and ensure that data is never lost. For our next component, we have a fan-out queue. Now let us quickly understand why do we need a fan-out queue. Suppose a user uploads a new post. Instead of immediately updating every follower's timeline synchronously, the feed service publishes an event into the fan-out queue. This makes post creation very fast because the user does not have to wait while the system updates thousands or even millions of followers. The expensive work is delegated to the background workers that we have. So the fan-out queue acts as a messaging layer between the feed service and the fan-out workers. Whenever a new post is created, it is placed inside this queue. Using a queue decouples the feed service from our workers. Even if thousands of users create posts simultaneously, the feed service simply keeps publishing events into the queue while workers consume them independently. This prevents sudden traffic spikes from overwhelming the system and makes the architecture highly scalable. Next, we have the fan-out workers. The fan-out workers continuously consume messages from the fan-out queue. Each worker processes one post at a time. Its first responsibility is to determine all the followers of the user who created the post. After identifying the followers, the worker writes the new post directly into each follower's cached newsfeed inside the cache memory. This is exactly what the connection between the workers and the feed cache represent. So the workers are connected to the feed cache as well. This technique is known as fan-out on write. So instead of generating a user's feed every time they open the application, we proactively prepare their timeline as soon as new content is published. Because of this, when followers later request their newsfeed, Redis or our cache memory already contains an updated timeline, making feed retrieval extremely fast. The workers also communicate with the SQL database. While cache memory provides fast access, SQL provides durable storage. The processed post information is stored permanently inside the database so that it remains available even if the cache memory is lost or it expires. Finally, the workers also send operational matrices to the monitoring and alerting service. These matrices include processing latency, worker failures, throughput, and queue processing statistics. Since the workers operate independently, we can increase the number of workers whenever posting traffic increases. This allows the system to scale horizontally without modifying any other component. The monitoring and alerting component that we have right here is a very important component, and every important component in our architecture must be connected to it. Both the feed services and the fanout workers send matrices to this monitoring component. Monitoring continuously observes the important system matrices such as request latency, cache hit ratio, queue size, worker failures, and many more. If any abnormal behavior is detected, alerts are generated so engineers can investigate and resolve these issues before users are affected. So this is our entire architecture, and let us now summarize the entire path. First of all, let us go through the read path. When a user opens the application, the client sends a request to the load balancer. The load balancer distributes the request across multiple instances, and the request reaches the API gateway where authentication and routing are performed. The request is then forwarded to one of the feed service instances. The feed service first checks the feed cache. If the feed exists inside our cache memory, it is immediately returned to the client. If it is not present, then the feed service retrieves the necessary data from our SQL database, constructs the user's timeline, and sends it back to the client. Now let us summarize the write path. When a user creates a new post, the request again passes through the load balancer, the API gateway, and goes to the feed service. Now instead of updating every follower synchronously, the feed service publishes a message into our fanout queue. The fanout workers consume these messages asynchronously. Each worker determines the followers of the author, writes the new post into every follower's cached feed inside Redis or our cache memory, stores the required information in the SQL database, and sends operational matrices to the monitoring system. As a result, when followers later request their news feed, the updated timeline is already available inside Redis and can be served almost instantly. Now we can run our architecture and see that it got approved because we met all our requirements that we had to meet. We can also check it out in Murphy's lab to test its performance, and once we exit Murphy's lab, we get a performance report of our entire architecture. Now note that we can scale up our architecture even more by adding more feed services, more fanout workers, but we had a budget constraint over here, and keeping this budget constraint in mind, this is the most optimal architecture that we could derive. So this is the basic design of an entire newsfeed system.